All right, this is for Haley and Libby. We're going to start 2-1, tangent lines and rates of change. All right, here we go. I'm going to read this paragraph because there's some good stuff in here. It says, many real-world phenomena involving changing quantities, like the speed of a rocket. Okay, why would the speed of a rocket be changing?
Because it speeds up.
Like it speeds up. Like it's not going to like instantly be going 300 miles an hour or however fast a rocket goes. I have no idea. It's not going to instantly be going that. So it increases in speed. Inflation of currency. It doesn't inflate at a linear pattern, right? It like goes up and then it comes down and whatever. Inflation. You know what inflation is?
Yeah.
Inflation. Okay.
Down.
The number of bacteria in a culture is not going to steadily increase because some die and then, some produce more rapidly depending on the food source of your bacteria, that type of thing. Shock intensity of an earthquake, voltage of an electrical signal, and so forth. In this chapter, we will develop the concept of a derivative, okay? Derivatives. Circle the word rate of change. A derivative is a rate of change. Derivative is rate of change. Boys, are you listening to this?
Yes.
Write this down. A derivative is a rate of change, okay? As in like velocity or acceleration, okay? I'll have you write down some other stuff. So I just mentioned velocity. When you're doing velocity, that is a first derivative. Acceleration, that's the second derivative, okay? A lot of times you will have, I guess, in front of the velocity, acceleration, yeah. In front of velocity, maybe I should put, sorry, I'm moving this down. I'm going to say the position function, okay? Position equals the original. So the way that this works is that, like, let's say I have the function negative x squared plus 16x plus 300. I have no idea, okay? What that's going to look like is a parabola starting at 300 and going down like this, right? Okay, so 300 is the y-intercept, and that means I'm like dropping something off of a cliff that's starting at 300 up in the air. Got it? And he's going down, all right? This is the equation of the position function, okay? What I can do is I can take the derivative of this, and it'll give me an equation, and I can find what the velocity is at any point in time. If I take the second derivative of that function, it will tell me what the acceleration is at any point in time, okay? So that's kind of how this works. You'll be given an original equation that has to do with the position of whatever object it is we're talking about. Velocity is the first derivative, acceleration is the second derivative, okay?
Getting deja vu from physics.
Yeah, probably. This has a lot to do with physics and that stuff, okay? So going back to like the limits and how we draw the limits into this. Eli, are you watching?
Oops. It's okay.
Drawing limits into this. So here's my original curve, whatever this curve is, okay? Maybe that's a bacteria in a petri dish or whatever, right? And let's say we want to find the constant rate of change, okay? Let me make this instead. Let's say that this is like my, I don't know. Let's say the distance from, I don't know, somewhere.
All I can think about is that stupid mystery thing.
Okay, let's say that this is my distance from somewhere. So like, let's say I have a red line and I'm increasing, I'm getting closer and closer and closer to a certain point, and then I'm moving farther and farther and farther away from that certain point, okay? So let's say that that's my distance. That's like the position that I'm at, okay? And right here, when I'm starting my journey, I want to know right here what my exact velocity is, okay? And what I can do is velocity is like a rate of change, right? Rate of change, okay? And a rate of change is the same thing as slope. And to find slope, I have this tangent line, and I can find slope of that tangent line. But I can only find slope if I have 2 points, right? So you remember way back when we started limits, I said, okay, let's do this. Instead of doing the slope with just this 1 point, let's do the slope between those two guys, right? Okay? And let's say for here, the actual slope is, let's say 2, but let's say here I get a slope of 1/2, right? Okay? And let's say instead, okay, my slopes aren't quite the same, but I'm going to move this point a little bit closer. So I'm going to do this point, and I'm going to find the slope between those two guys. Is that going to give me my exact slope that I'm looking for? Or my exact speed? No, but it's going to be closer than what it was before. So this might be like 1 exactly, right? So then I do another point that's even closer, and I do another tangent line, and I keep moving that point closer. Let's say this slope is 1.5, right? 1.5. And I keep moving it closer and closer and closer, finding that limit, okay? That's kind of like when we start plugging numbers in on the left or the right side, like your limits of like 10 plus or 10 minus, right? On the left or the right side to try to figure out what that value is approaching. Got it? So like this is kind of like a hole here. We're trying to find what that y coordinate should be or what that slope should be, okay? And that's how we do it, okay? So what they have going on here is the slope of PQ, which is the secant line. I'm going to put secant here, okay? And the way that we do that is we do f of x, whatever our function is, minus f of x naught, okay? X naught is the point that we're interested in, okay? Like this, where he's touching the tangent line. X naught is the point for our tangent line, okay? And f of x naught is like the y coordinate, right? The y coordinate for our tangent line, x naught on the bottom, this is the x coordinate for our tangent line, okay? So these x and y coordinates right here, this is the place that we're looking at finding the slope at, okay? We do the whole thing, yep. Okay, so we're looking at a slope, we're trying to find, and we're subtracting those, okay?
Wait, so the y coordinate is the top guy?
The y coordinate, because it's y2 minus y1 over x2 minus x1. This is basically what it is, right? y2 minus y1, x2 minus x1, if that helps you to think about it that way. That's how this works, okay? All right, I'm going to skip the definition. Let's go down to the first example right here where it says, use the definition. We are finding the limit. I'm going to write this down. The limit as x goes to x naught. So as we get closer and closer and closer to our original point, this is the original point. This is our slider. Okay, x is the slider, x naught is the original point. What? What? What are you talking about?
You said slider, my brain.
Okay, sure. Oh, Lordy child.
Oh my gosh. I'm sorry.
Over x minus x naught. This is the formula that we use, okay? This is slope right here. This is how you find slope, right? y2 minus y1, x2 minus x1. So our original point is x naught, like that's where the tangent line point is, and then x is the other point that we're using. We're trying to get closer and closer and closer to that. So this is saying as x gets closer to x naught, what's happening, right? As x gets closer to x naught, what's happening, okay? So use the definition to find an equation for a tangent line. Our function is this parabola, y equals x squared. And I want at the point 1, 1. Those are the two pieces of information it gives me, okay?
That whole thing is
There is that. What? This whole thing is the slope right here.
Okay.
Yep, we're using the formula for slope basically, okay? All right, so our function, you'll be all right. It'll be all right. Okay, y equals x squared. This is like saying f of x equals x squared, right? Got it? Okay, that's what f of x is. So when we go to plug stuff in, f of x is x squared, right? Got it? I'm going to write it down here. X squared over, okay?
What?
F of x naught, okay? Our f of x, our function right here, y equals x squared, that's f of x equals x squared. So if I say f of x, I'm just putting x squared in that spot, right here, in that first spot, okay? All right, minus f of x naught, okay? What's x naught going to be? Yeah, it's like the x coordinate of the dot that I'm looking at. This is my x naught, okay? So what I'm going to do is to find f of x naught, I'm going to plug 1 in, right? If I plug 1 into x squared, what do you get? 1, okay? And then I'm going to do x minus x naught, and x naught is 1. Okay, now, x naught right here, so what I'm trying to do, let me write this over here. I'm running out of room. The limit as x goes to x naught, we've plugged all of our stuff in, and we have x squared minus 1 over x minus 1. Now, the only other thing that I have to do is, what was x naught here again? What was our original x, the point that we're looking at? 1 right here, okay? So we're plugging 1 in. So I want the limit as x goes to 1 of that stuff. What's the problem?
We can't do that.
We can't do that, okay? But we know from limits, that's a hole, right? We know from limits that this guy can be broken down. So I want x plus 1 and x minus 1. And I can cancel out my x minus 1s. So now all I have to do, limit as x goes to 1 of x plus 1, and the slope is 2.
Sorry.
You're fine, you're fine, you're fine. The slope is 2. Got it?
So, you said that
So,
sorry.
Go ahead, keep going.
Like last year, you said you started with this. How would you do this without learning limits? Didn't you start with this?
No, we started with limits. Yeah, we started with limits, but we didn't start with limits until like right before Christmas break. That's what we did, right?
Okay.
So up until Christmas break, we were doing like algebra stuff and like rational functions and doing the ha's and va's thing and like talking about those and then finally introducing limits. Yeah,
Okay.
that was the deal. So
Alright.
we just had a lot more algebra review stuff before we hit limits. So yeah, you still have to do limits before you introduce derivatives. Yep. So what's happening here is it's saying, I'm going to draw a picture of this if you want to draw it as well. Here's what it looks like. This is what x squared looks like. This is my original, let me make him better. This is my parabola, right? Y equals x squared. Okay? At the point 1, 1, this guy right here, if I draw a tangent line, what do I know about that tangent line? He has a slope of 2, right? By using this formula, by using that function.
A lot of work just to find.
Right.
Wait,
But
so-
it won't always be that hard.
Okay.
I will show you. Eventually, we will get to a point where we can just look at this guy and just look at this guy, and we don't have to do a limit anymore. All I have to do is say the derivative's 2. Because the derivative of x squared is 2x, and all I have to do is plug 1 in.
I remember you guys doing that
Yep.
last year in class.
It's really
when
easy.
we were, like,
So
struggling.
this is the way of finding a derivative using the limit process, right? And then eventually we'll get to the point where we can just do derivatives by using what's called, so I used what's called the power rule to find the derivative of x squared.
So if
It's really
x to
easy.
the fourth, you take 4 times whatever x is.
Kind of. X to the 4th, his derivative is 4x to the 3rd.
Why did you put a 3 up?
What?
there?
Absolutely.
Why?
You drop the exponent down in front and subtract 1 from the exponent. That's how you find it. You just learn the power rule. There you go.
I like that.
Okay?
Well,
You're gonna love derivatives. After we get through the icky limits stuff, we've got to bridge the gap between limits and derivatives, but after we get past this icky stuff, you're gonna be like, yes, derivatives are awesome. Okay, so let's go to this way. So what we have going on here, this is a different way of writing what we just did, which was the limit as x goes to x naught.
Where did we get an H?
I'll show you. F
why
of
are we
x
doing tangent?
minus f of x naught. I'll show you here. What? Tangent?
Yeah.
Oh. Not don't think of sine, cosine, and tangent. Tangent line is different than tangent.
Why? Why?
They're two different tangents. Okay, we'll get to that.
What is tangent and
Why?
secant? Tell me that
'Kay.
it doesn't, like,
Tangent and secant have nothing to do with sine, cosine, tangent, secant, cosecant, cotangent. I don't know. Okay?
so
Secant, a secant line, not like the secant function. There's a secant function, then there's a secant line. A secant line is a line that crosses through a equation at 2 places. A tangent line, not tangent as a function, not sine, cosine, and tangent, but a tangent line is a place that only touches one place, okay? So the way that I think of like tangent lines is like on a bicycle.
Shut up.
Okay, you ready? On a bicycle, you have like the gear here, and then you have a gear here, and like he's touching here, and he's going across, and he's touching here at the top. Those are like tangent lines because they're only touching at one place, right? Where he stops and leaves the thing, and then he goes around this way. But anyway, this line that goes all the way through here is a tangent line because he's only touching at one place. Okay, he is the instantaneous rate of change. Okay, tangent line is an instantaneous rate of change. It's just at that exact moment, what's my velocity, or like how fast am I going? At just that exact moment, at just this place right here, what's my velocity, etc. Okay?
What did you say?
What? Instantaneous rate of change. Like I can talk about rate of change, and I can talk about average rate of change. So like from here to Lincoln, I'm going an average of 62 miles an hour. If I average out my distance over time, right? Velocity equals distance divided by time, or distance divided by time. Okay, so if I average that out, I was going 62 miles an hour. But at like 3 miles outside of Hastings, what speed was I going at that exact moment? Right? What speed was I going at exactly at the moment I hit the mile marker 371? What was that speed exactly? So I'm talking about instantaneous rate of change instantly at that point. Not average rate of change. If I average it all out, I was going 62 miles an hour the whole time, right?
Secant.
But exactly at that point. Secant is just helping us get to tangent. We don't care about secant. Secant is just like, I have to do secant because I have to have 2 points on my line, right? In order to find slope, y2, y1, x2, x1. I have to have 2 points in order to find the slope of a tangent line, or just like the slope of that one point, right? Slope has to have y2, y1, x2, x1, right? But here I don't have that on my tangent line. I have just one place, instantaneous rate of change, that one spot. So what I'm doing is I'm using the secant line, and I'm gonna swivel him a little bit closer every time to try to get him closer to what the exact is, like the limit does, right? Okay, you guys remember filling out the tables where it was like, find what the value is at 3 exactly. So we would plug in like 2.9 and 2.99 and 2.999, right? We're getting really, really, really close to what the exact is without actually hitting the exact, because we can't, right? Okay, or we would plug in like 1.99 or what was it, 3.01 or 3.001 or 3.0001. We're trying to squeeze in on either side to try to get to that point without actually touching that point, right? That's what the secant line does for us. It's just, the secant line is used to approximate what the tangent line is. And tangent line is instantaneously at this point, how fast am I going? Because we can't find it if we don't have 2 points.
Got it.
Right? Until we know how to do the power rule, which you guys kind of already do, I guess, right?
Bring it to the front, subtract by 1.
Mm-hmm. Yeah, that's the power rule. Okay? Got
Do
it?
we have to do that if we know the power rule?
Let's do one more. Let's do example 2 and then we'll stop.
So
Okay.
is that one the opposite?
Just to bring it full
Is that
circle.
x squared?
What?
So is that the same as y equals x squared? Or the square root of x? That one there, for example 2, with the 2 divided by x?
Yeah.
With 2 multiplied by x, that is squared. So would we take the square root of that instead?
No.
We have to write another essay.
No.
That's where we have to use something other than the power rule for. Yeah.
This one's only 3 to
Yeah,
4
kind of.
marks,
Okay, so find the equation of the tangent line. All right, so here we go. Here's our equation. I'm going to call him f of x. This is the information that it gives to us, is 2 over x. And our point is 2, 1. So I want to know what the slope is at 2, 1. Okay, we're going to cheat and we're going to look at this. Okay, this is 2 over x. This is what he looks like. He's a boomerang, right? And at the point 2, 1, which is right here. Okay, I want to know what the equation of this guy is. Okay, when they say equation of tangent line, I'm going to circle equation and I'm going to circle line, and those two things. Okay, what's the equation of a line? Y equals mx plus b. That's what we're looking for. Okay, we're looking for the equation of a line. All right, so they already have it solved for you over here. This is what we will get to, but I'm going to show you how we're going to do this. Okay, so I'm wanting the equation of this line. The answer is this, right? I'm going to show you how we get to that. Okay, negative 1/2 x plus 2. That's what we're getting to. Okay, we have to do the derivative, which is the limit. That's this thing as x goes to x naught of f of x minus f of x naught over x minus x naught. That's what we have to do, okay? We have to do that thing to find the slope, which is m. That's what we have to do to find m, right? Okay, so what's our answer going to be? Negative 1/2 right here. That's what we're looking for. That's what this thing is going to give to us. So we know what the answer is. I'm going to show you how we get to that. Okay, ready? We know the answer should be negative 1/2. All right, so the limit, we're going to fill our stuff in. As x goes to, what is x naught? What's the original x of the point? Yeah, 2. So we're going to 2, okay? And then we just need f of x, okay? What is f of x?
1.
No.
2 what?
X.
F of x is this function right here. 2 over x, right?
Ew.
You see that? 2 over x, that function, minus, okay, now f of x naught was 2, right? And now I plug 2 into there. What's that? 1, okay? Over x minus x naught, so x minus 2. X naught is 2, right? Okay, so these guys are kind of like just chilling out until we do our x naught thing, right? We're doing our x naught thing.
Now I plug 2 in, right?
Okay,
So 1 minus 1 is
hold
1.
on, hold on.
They're both zeros. On the top and
Yeah,
the
so we
bottom.
can't do that. What?
Why does it say when we started that this is the y coordinate?
What?
The f of x.
What you talking about?
On my notes.
I hear what you're saying. That's
It just says y coordinate on mine.
Oh. We're finding the y coordinate. We're finding what f of x is. I see what you're saying. Maybe I shouldn't write it like that. Like we're trying to find what the output value is. Maybe I should say instead of y coordinate output. The output value when we plug it into our function. Does that make sense?
So is f of x then?
I guess.
Is f of x the equation then?
Let me go down.
Is that what I figured
I mean, I guess it still is the y coordinate. Yeah, we got y that from there, right? The y coordinate. That's still gonna be the y coordinate.
So you could just plug in.
So you could just plug in this, right?
That's yeah.
Yeah,
that's what
yeah,
we're
that's
trying
fine. Yeah, yeah. We could write it like that. We could think about it like that.
to- Okay.
Yeah, yeah,
So
yeah.
if that like number was like 2,
And this
5,
is 2.
You don't
But-
plug it in. You
F
just,
of
No.
X is always
You could just
the
put 5 into what?
okay, I get
F
that.
of X is the equation.
What? Yes, yes. F of x is the equation. Okay, so now I have to figure out how to find the limit of this. We got to do some finagling. Can we plug in 2?
No. It's
No.
zero on the bottom.
We got 0 on the bottom if we plug 2 in. So how are we gonna do that?
Alright. I don't know.
Flipper flopper.
I don't even have that written down actually.
You can't even divide 0 by 0.
Nope, it's called the indeterminate form. We don't want that. What shall we do? What shall we
Well,
do?
2 over 2 is 1, and there's 0 over 0, 1.
Can we multiply the whole thing?
By
2. Negative 2.
Or but don't you need to put the fraction on the bottom or something?
Can we multiply it though? Do
What?
we just need to figure out what to multiply by?
I'm
Really
really
What do you mean?
multiply
Am
everything
I on
by
the right
negative
track?
2.
Negative 1.
Multiply everything by negative 2.
Negative 1.
multiply everything by negative 1, you
Why
said?
are we doing that?
Well, we want 2.
But then that's gonna change the.
fraction out.
That's not gonna work. We want to be able to plug 2 in, and I can't right now.
I want to get the fraction out of there.
You want to get the fraction out of there? Okay, so let's do.
How about wait? What is it? Our steps?
Possibly. I mean, it could.
What steps could you do?
Well, we try plugging in. It can't work. What was the next one?
Try to eliminate out a
Factoring?
whole, or like
Factoring?
factor it.
No.
Can you do that?
I don't know. I don't know.
Take like an
Can we
x
split it up?
minus 1
Can you split it up?
situation.
The only other thing I can think of is like make this x over x. Let me do a different color. Make this x over x, right?
What?
Does
that make sense?
X
So
over
this
X.
top would really be like 2 minus x over x. Like if I made the whole thing, all over x minus 2. You see that?
Oh. Wait,
No?
What is
Where did we
x
get
minus x?
Where do we get x
On
over
the
x?
bottom.
She just
Oh wait.
No, no.
Never mind.
We were
Don't
combining the
subtract
bottom, like combining this as a common denominator,
Subtract bottom.
right? To make that. So 1
But
is
you
like
can
x over
multiply
x.
the bottom by negative to crisscross. To like
Now can we
eliminate.
flip it over?
Okay, let's try it. I don't know. Let's try it. Let's flip this. Okay, so what's this guy as a fraction?
How
This guy would be over 1, right? Okay, if we flip him to the top, we're multiplying by 1 over x minus 2, right? Like that. Does that cancel with 2 minus x?
Multiply it by negative 1.
Okay, so let's pull out. I got it. You're right. Look at this. Okay, so do you see where we're at this point? We're right there.
No.
No.
I'm so
Okay, okay. Do you see how I got from here to this step, from
No,
this step
I'm
to this
so
step?
confused why it's x over x. I
Okay,
don't
'cause
get
it's
that at
1.
all.
Okay, okay, okay.
like,
Let's
if
back up.
you
You're
say
fine.
you
You're
plug
fine.
in 3 for x, it's gonna be 3 over 3, which is always 1. You understand that?
Oh, okay, because it's the same number. Okay.
Yeah, yeah, yeah.
that was
Okay,
the
so do we
dumb-
get x over x? We see how we got that?
Yeah.
Okay, so I've got this. If we put it together, I have a common denominator of x on the bottom, and this is 2 minus x on the top.
You can do. Oh, yeah. 'cause
Yep,
you subtract.
Right? Yep, yep. And then we've got x minus 2 on the bottom. Got it. We're almost there, guys. This is over 1, right? If we
actually
make
doing
that a
the right
fraction and a
thing.
fraction, okay? Now we're going to flip this to the top, and we're going to multiply by 1 over x minus 2. Okay? Now, Josie said, okay, let's try to cancel those, but they're not the same. Right? So let's do this. Let's pull a negative 1 out of this thing.
Oh.
You can do that.
Yeah, you sure? Why not? This would be negative 2 plus x. Is negative 2 plus x the same thing as x minus 2?
Yep.
Now can I cancel those?
Wait, I need to write this down.
Wait.
Okay, let me back up.
Are we multiplying the whole thing by negative 1 or just?
We're just pulling a negative 1 out front.
For which
For
one?
right now. He's just going
Why
to sit
can I
there.
do that? Why
Hold
can
on.
you do that?
Hold on.
Because you're not like dividing anything by a negative. You're just pulling it out in front. You're just writing it differently, right?
It's
Yeah?
the same guy, it's just different.
Yeah.
Gross.
Just so I can make him cancel?
understand what I'm
Wait,
writing
I'm
now.
trying to make this.
Okay.
coherent.
You tell me what you need me to do.
Negative 2 plus x over x.
So wait, what do we have now?
Over x.
Okay? All right, we're so close to being there, guys.
Subtract, cross out.
All right, I'm going to cross that out. So let's write what we have left over.
Negative 1 over x.
Negative 1 over x. And we're trying to find the limit as x goes to
Yay, we can plug it in.
2.
Wait, 2 minus x over x. 2.
Negative 1/2.
This crosses out with this. What did we do?
We're so smart. We're so smart.
Well, I mean, that was given to us in the beginning. We didn't have to do all that.
So
but,
it's-
you know.
Well, I know, but you won't be given that. That's the
Yeah,
that's the
you're right.
point. So I'm just showing you like this is what we're trying to get to, so we know that we got the right answer, right? Okay, questions about where we're at now?
It's
Okay, do you see where we keep flipped this to the top?
Yeah.
Yep, and now I pulled a negative 1 out, and now I'm going to cancel that with this. So on the top, I have negative 1 times 1, which is negative 1. On the bottom, I have x, which is x. And now I plug a 2 in, and I can, because there's no 0 on the bottom, so negative 1/2.
We might need to go over
We're
that.
gonna. We will. You betcha. I'll start from scratch. So now that you guys have it all written down, now you can just, like, watch. Okay? All right, so we have the slope. Now we got to get the rest of the equation on tomorrow. On tomorrow. Goodbye.